Take a second and think about what you're actually standing on right now. Dirt, rock, broken down plant matter, crushed minerals, tiny bits of things that used to be something else. None of that sounds particularly hard. Dirt crumbles in your hand. You can dig through it with a spoon. So why does the ground feel like concrete under your feet? Why can you fall on it and break a bone when the stuff it's made of seems like it should just give way? This question sounds simple, almost like a kid would ask it, but the answer touches on some genuinely wild physics. Once you understand it, you'll never look at the ground the same way again. Let's start with the obvious answer, the one most people land on without thinking too hard. You might assume the ground is hard because it's packed tightly, and that's true, but it's only the beginning of the story, because packed tightly still doesn't explain why you can't just push through it. After all, a pile of sand is also packed tightly in places, and you can still shove your hand straight down into it. So tightness alone isn't the whole answer. The real answer starts at a scale way smaller than dirt particles. It starts at the level of atoms. Every solid thing you've ever touched, the ground, a table, your own bones, is made of atoms, and atoms are mostly empty space. And this part tends to blow people's minds the first time they hear it. If you could shrink down and look at a single atom, the nucleus in the center is unbelievably tiny compared to the space around it. If an atom were the size of a football stadium, the nucleus would be smaller than a marble sitting at the 50-yard line. Everything else, all that space around it, is where the electrons live, buzzing around in a cloud. So if atoms are almost entirely empty space and the ground is made of atoms, shouldn't you just fall straight through it? This is actually a legitimate question physicists get asked all the time, and the answer comes down to something called the Pauli exclusion principle, plus a force you felt your entire life without knowing its name: electromagnetic repulsion. Here's the simple version. Every atom has electrons on its outer edge, and electrons carry a negative charge. Negative charges push away from other negative charges. When you press your foot down on the ground, you're not actually touching the ground in the way you think you are. The electrons in the atoms of your shoe or your skin are getting close to the electrons in the atoms of the dirt and rock beneath you, and those electrons repel each other hard. That repulsion happens incredibly fast and incredibly strongly at short distances. What feels like solid contact is actually a standoff between electron clouds, pushing against each other so forcefully that neither side gives up ground, so to speak. This is why you can't push your hand through a table, why a bowling ball doesn't sink into a sidewalk, and why the ground holds you up instead of swallowing you. It's not that there's no empty space, it's that the electromagnetic force guarding that empty space is stronger than anything your muscles can produce. Now that explains why solids resist other solids in general, but it still doesn't fully answer why dirt, specifically loose and crumbly as it looks, ends up feeling like pavement under your feet. For that, we need to zoom back out to the particle scale. Picture a handful of loose soil. It's full of gaps, tiny pockets of air between each grain. If you just scoop it up, it feels soft, because there's nothing holding those grains together in a fixed structure. They can slide past each other freely. But the second that same soil gets compacted, whether by rain packing it down, by years of foot traffic, or just by the sheer weight of everything sitting on top of it, those grains lock into place. They wedge against each other. Every grain is now resting against several neighbours, all pressing in from different directions. And every one of those contact points is another spot where electron clouds are repelling each other and holding the line. Once you have millions of these grains wedged together, all locked at slightly different angles, the ground stops behaving like a pile of loose particles and starts behaving like a single connected structure. It's a bit like the difference between a stack of loose bricks and a wall that's been cemented together. Same bricks, completely different behaviour because of how they're locked into position relative to each other. This is also why wet sand at the beach feels firm enough to walk on, while dry sand near the dunes feels like it swallows your feet. Water pulls the sand grains together through something called surface tension, packing them tighter and locking them into a denser structure. Add too much water though and you get the opposite effect. The particles start floating apart in the liquid instead of locking together, which is exactly what's happening in quicksand. It's not that quicksand is unusually strong, it's the opposite. The grains have lost their grip on each other completely. So there's nothing solid to push back against you. You're not sinking because it's grabbing you. You're sinking because there's nothing there to hold you up. So the ground you're standing on right now sits somewhere on a spectrum. On one end, you've got loose, ungripped particles like dry sand or fresh soil that give way easily. On the other end, you've got tightly wedged, densely packed material like compacted earth or solid rock, where every particle is braced against its neighbours and none of them are going anywhere. Most solid ground you walk on every day sits much closer to that second end, especially anywhere that's been walked on, rained on, or sat under pressure for years. Even there's another layer to this too, and it has to do with pressure and time. Deep under the surface, soil and rock experience enormous pressure from everything sitting on top of them. That pressure squeezes out the air gaps between particles and forces them into incredibly tight arrangements. Given enough pressure and enough time, loose sediment actually turns into solid rock. This is literally how sedimentary rock forms. Layers of sand, mud and organic material get buried, compressed under the weight of everything above them for thousands or millions of years, and slowly fuse into something you'd never guess started out as loose grains you could run your fingers through. So when you're standing on solid ground, especially anywhere with a long geological history, you might genuinely be standing on what used to be soft material that got crushed into rock over an unimaginable stretch of time. Now here's a question worth sitting with for a second. If the ground is holding you up because of electron repulsion at the atomic level, why does anything ever sink, break or crumble at all? Why isn't every surface equally solid? The answer is that this resistance has limits. Electron repulsion is powerful at short range, but it's not infinite, and it's only as strong as the structure holding those atoms in position. If you apply enough force, more than the bonds between particles can handle, the structure breaks. And this is exactly what happens when you fall and break a bone, or when a sidewalk cracks under a tree root, or when a car tire compresses concrete hard sand into a different shape. You're not overcoming the atomic repulsion itself. You're breaking the physical connections holding a bunch of atoms together in a particular arrangement. And once those connections snap, the material rearranges into a new, often less organized structure. That's what breaking really is at a fundamental level. It's a structure losing its grip on itself. This is also why some solid feeling things are actually much weaker than they seem, and why some soft looking things are stronger than you'd expect. Chalk feels solid but crumbles under light pressure because the particles inside it are only loosely bonded. Meanwhile, something like packed clay can feel almost as hard as stone because its particles are locked into an incredibly tight water-bonded structure. Hardness isn't really about what something is made of, it's about how tightly and how completely its particles are locked against each other. So let's bring this all the way back to the original question. Why doesn't the ground feel soft if it's just dirt? Because just dirt is doing a lot of hidden work in that sentence. Dirt isn't one simple uniform substance. It's billions of individual mineral grains compacted over time, pressed together by gravity and rainfall and foot traffic, locked into a structure where every single particle is being held in place by the same electromagnetic force that keeps your hand from passing through a wall. What looks like a soft, crumbly material from a distance is actually an enormous, densely interlocked network, held together one microscopic electron standoff at a time. The ground isn't hard because dirt is secretly a hard material. It's hard because of what happens when enough of it gets pressed together, locked into place, and given enough time to settle into a structure that doesn't want to move. Every step you take is being caught by an invisible force, working at a scale smaller than you can imagine, doing its job so reliably that you never even think to notice it, which honestly might be the most impressive part. The most important physics happening under your feet all day is completely invisible, completely silent, and somehow still stronger than anything you could ever push against it.